everybody. We're getting ready to do lesson 10.2, part 2, pre-calculus math today. And for vectors in space, part 2, you got 4 points here into your notebook. And 32 points will go on to your classwork sheet, which you should have in front of you. In my classroom, name, date, period, homeschoolers and onliners, put your due date here. And let's go right into slide 1. Parallel vectors. So recall from the definition of scalar multiplication that positive scalar multiples of a non-zero vector v have the same direction as v, whereas negative multiples have the direction opposite that of v. In general, two non-zero vectors u and v are parallel when there is some scalar c such that u equals cv. For instance, the vectors u and v and w are parallel because u equals 2v and w will equal negative v. So in this situation here, they're parallel because u equals 2v, u equals 2v, and then w here equals the negative of v, so it's moved across here. So this is how they will be parallel because of scalars. Okay, knowing that little bit of information, parallel vectors. Vector w has an initial point of 1, negative 2, 0, and terminal point of 3, 2, 1. Which of the following vectors is parallel to w? So, okay, so we got a here, u equals 4, 8, 2. Is this parallel to this vector w up here? Begin by writing w in component form. So w, when we write it in component form, we come up with 2, 4, 1. 3 minus 1, 2 minus a negative 2, and then 1 minus a 0. So it becomes 2, 4, 1, the component form of this vector up here. A, because u equals 4, 8, 2, this is u here. W, remember, is 2, 4, 1. And w is 2, 4, 1. So if we multiply w by 2, we get 2 times 2, 4, and 1. Guess what? We get equals 2w. So u will equal 2w. Therefore, you can conclude that u is parallel to w because of that simple fact here. It has by a scalar, it will become the same thing as u. Okay, so now for B example, b equals negative 1, negative 2, negative 1/2. So because v equals negative 1 and negative 2, negative 1/2, and this, by the way, if you take 1/2 of w, which is 2, 4, 1, you will get this here. You will get v. If you take a negative 1/2 of w, you will get the same component form of a vector. So therefore, you can conclude that v is parallel to w. Okay, let's try another one. Z equals 4, 8, 4. In this case, you need to find a scalar c such that 4, 8, 4 will equal 2, 4, 1. However, equating corresponding components produces c equals 2 for the first two components and c equals 4 for the third. So the third equation has no solution, and the vectors z and w are not parallel because of that fact. Okay, let's try one. Determine whether u and v are orthogonal, parallel, or neither. So we got u with this, and we got v with this, negative 12, 6, 15, 8, negative 4, negative 10. So a negative 3/2 of v will equal the negative 3/2 of 8, negative 4, negative 10, which is 12, negative 12, 6, and 15, which equals u. So therefore, they are parallel. So u and v would be parallel because they have a scalar of -3/2, which will yield parallel lines. This one down here, students, I want you to do that one on your own. Let's move on now to the next one. You can use vectors to determine whether 3 points are collinear, meaning they lie on the same line. The points P, Q, and R are collinear if and only if the vectors PQ and PR are parallel. So collinearity will also contain the property of parallelism within collinearity, right? That sounds about right. So using vectors to determine collinear points. Determine whether the points P, which is 2, -1, 4, Q, which is 5, 4, 6, and R is -4, -11, and 0. Which one are any of these collinear with each other? So the component forms of PQ and PR are PQ, you'll come up with this component form of a vector 3, 5, 2, and PR you'll come up with -6, -10, and -4. So knowing that, because the vector PR equals the negative of 2PQ, you can conclude that they are parallel for the points P, Q, and R lie on the same line as shown. So here would be a graph of PQ, vector PQ, and then PR is right here. PQ is here. So they are collinear because they show parallelism. So, and then when you graph them, you find out that indeed they are collinear. So in these exercises, use vectors to determine whether the points are collinear. So we have 1, 3, 2, -1, 2, and 5, and then 3, 4, -1. So in this situation here, for 57, students, I'm going to let you do this one on your own. For 57 up here, we have V equals -1, -1, 2, -3, then 5, -2. So here will be the component form here of -2, -1, and 3. And then U would be 3 minus a -1, 4 minus 2, and then -1 minus 5 will be 4, 2, and -6. Since U equals a -2V, the points they're at least parallel, and they are collinear in this situation here. So that's the one way of showing collinearity. Finding the terminal point of a vector. The initial point of the vector V is 4, 2, -1. V equals that and is P. So that the initial point of V equals 4, 2, -1 is P3, -1, and 6. Let's say this again. The initial point of vector V is 4, 2, -1 is P of 3, -1, and 6. What is the terminal point of this vector? So the initial point of vector V, 4, 2, -1 is this. Now here is a component form. So this will be a point here is P3, -1, and 6. This is the initial point here. What is the terminal point of this vector? Since we have the initial, and then we have the component form. So using the component form of the vector whose initial point is P, which is 3, -1, and 6, and whose terminal point is, we don't know yet, Q, Q1, Q2, Q3, you can write vector PQ equals Q1 minus P1, Q2 minus P2, and then Q3 minus P3. So when we plug in our values here, 3, 1, and 3, will actually be 3, -1, and then positive 6. That way we need to find Q1, Q2, Q3 so that it equals 4, 2, and negative 1 as a component form. To do that, how do we get there? So this implies that Q1 minus 3 equals 4, Q2 plus 1 equals 2, and then Q3 minus 6 equals negative 1. So the solutions of these three equations are Q1 equals 7, Q2 equals 1, and then Q3 will equal 5. So the terminal point would be 7, 1, and 5. So using that kind of technique here, the vector v and its initial point are given. Find a terminal point. So we have the initial point here, 1, 5, 0, and then we have a component form of the vector 2, negative 4, and 7. So to find a terminal point, we have v again equals 2, negative 4, and 7, q, which will equal q1 minus 1, q2 minus 5, q3 minus 0. So we have our three equations here. 2 equals q1 minus 1, negative 4 equals q2 minus 5, and then 7 equals q3. So q1 will equal 3, q2 will equal 1, and then q3 will equal 7. So terminal point would be 3, 1, and 7. So using that technique down here, students, you have your initial point, and then you have a component form. So you need to find your terminal point, knowing these two facts here. And that is 10.2 Part 2 lesson, classwork lesson for pre-calculus math. If you need course materials or you have any questions, email me, animatedpowerpointmathvideo@AOL.com. Thank you very much.